in progress.
So this is video 2. This is 2.3. I'll say video B. How about that? So this is on limits of polynomials and rational function. So let's say P of X and Q of X are polynomials. That's a Q. Don't look like a Q. There we go. Which kind of makes P of X over Q of X. This is a rational function because we have a fraction. It's a ratio. So for any polynomial, the limit as x approaches a of P of X equals P of A. The same obviously is the same is true for Q of X. It's just a different letter of the function. Q of X equals Q of A. And when we look at the rational version, limit as x approaches a of P of X over Q of X, we get P of A over Q of A so long as Q of A does not equal 0. My Q looks a lot like a G. Okay. So we had this problem right up here, the x squared plus 3x plus 1 over x cubed plus 2. Let's redo that one. Let's redo the one we had above using our new limit law. Limit as x approaches a of, what was it? X squared plus 3x plus 1 over x cubed plus 2. Oh shit, I don't want to do a. That's the generic form. We were going towards -1. We're going towards -1. So this is like a P of X and this is like a Q of X. So we just plug in the -1. This is -1 squared plus 3 times -1 plus 1 over -1 cubed plus 2. And you're going to see that when you do all that math again, we get -1. And it's a lot quicker than doing all this mumbo jumbo stuff we did up here in the green. We broke it down step by step. For all polynomials, this is good. Maybe I better mention what a polynomial is, just so we're all on the same page. A polynomial is, we can have a sub n x to the n plus a sub n minus 1 x to the n minus 1. We keep going down, a sub 1 x to the first power plus a sub 0. The a sub stuff are just numbers, coefficients. I need to give myself more room to write. Why did I do this? Quit trying to squeeze stuff in, David. Let's put this down here. Where an minus 1, etc., a1, a0 are all just constants, i.e. coefficients. That's a polynomial. Notice the exponents are all integers. Greater than 0. Well, greater than or equal to 0. A sub 0 has a... This is like having an x to the 0, right? Because x to the 0 equals what? 1. All right, let's take a look at that one was kind of easy. What about when we have stuff like this? Limit as x approaches 3 of x squared minus 9 over x minus 3. Now that's a p of x and that's a q of x, so we sorry about that. Let me turn off my ringer. I thought it was off. So we should be able to just plug it in, right? It is off. Spam makes it through the ringer. What bullshit. If I plug that in, I got 3 squared minus 9 over 3 minus 3. I get 0 over 0. Uh-oh. Like 0 over a number is 0, but a number over 0 is DNE. So what the fuck is this? So remember all that stuff you've been doing for the last 3 days and you're like, why the hell are we doing it? This is where it starts kicking in, folks. We're gonna factor this. We're gonna do limit as x approaches 3. The top is a perfect square minus another perfect square. It factors to x minus 3 over x plus, or times x plus 3. And this is x minus 3 on bottom. Now we can cancel this stuff out, leaving behind a 1 on top, 1 on bottom. And this gives us a limit as x approaches 3 of x plus 3. And now we just plug it in. We get 3 plus 3 equals 6. So like if f of x equals x squared minus 9 over x minus 3, f of 3 DNE, it doesn't exist. But the limit as x approaches 3 of f of x equals 6. This is doing something where it's making a hole in the graph at 3. So this is like a line going like that. There is a hole. This is what happens when you can cancel out the bottom. When you can cancel the problem on the bottom. I'm going to hit you with some cool calculus buzzwords. This is called a removable discontinuity. In 2.4, we're going to talk about continuity. That's next week. Basically, a discontinuity is where there's a hole, or where the graph doesn't exist. I'm gonna leave it at that. There's a better definition in discontinuity, and let's just go with the buzzword of removable discontinuity for now. Okay. So a general strategy for these. So strategy when that's not how you spell strategy. for limit x approaches a of f of x over g of x ends up going to 0 over 0. Well, first off, plug it in to see that you get 0 over 0. Plug a in. And then the following things we can do. Try factoring and canceling. Like we did right up above. Canceling common factors. Then B. If the numerator and denominator and or denominator, let's say or denominator, has a difference, kind of like x minus c or something like that, something weird. But it has a square root, or x minus square root. And I hate writing numerator denominator because they take a long time to write. I always call this top and call this bottom. What we're going to do is we're going to multiply top and bottom by the conjugate. The conjugate would be square root of x plus c for the top one, or x minus the square root of c for the bottom one. It's usually not this. Usually not this one. Let's just say a plus. Square root of c is generally not a problem. It's usually when the square root is on the x. We'll look at an example of that in a second. And if f of x over g of x is a complex fraction, simplify it. Okay. So, example 1, limit as x approaches 3 of x squared minus 3x over 2x squared minus 5x minus 3. If I try plugging in 3, I get 3 squared minus 3 times 3 over 2 times 3 squared minus 5 times 3. I said minus, but I wrote plus. This is 9 minus 9 over 18 minus 15 minus 3. This gives us the 0 over 0 problem. So what we're going to do is factor top and bottom and see if anything cancels. The top factors into x times x minus 3. The bottom, if you go through factoring it, you're going to get 2x plus 1 times x minus 3. Now the x minus 3's can cancel. And we get limit as x approaches 3 of x over 2x plus 1. And now if I plug in the numbers, I don't have a problem. I get 3/7. So it does actually approach a value. Okay. Next one. This will be one with a root in it. Limit as x approaches 5. Square root of x minus 1 minus 2 over x minus 5. If I try plugging in 5, I get 5 minus 1 in the radical minus 2 over 5 minus 5. This is 2 minus 2 over 5 minus 5 is 0 over 0. So what we're going to do, I'm going to rewrite it. And I'm going to multiply the top and the bottom. I'm going to put these in parentheses. And I multiply this by x minus 1 plus 2. And when I multiply the top by that, I have to multiply the bottom by that. So this ends up being limit as x approaches 5. This is, and I'm going to leave this stuff on bottom factored out. We're not going to multiply it out. I know a lot of you kept wanting to multiply it out in class. Don't do it. The top turns into this because it's a difference of squares. So this top, and make sure you keep writing. Notice I keep writing limit every single time. Don't stop writing limit because it's wrong if you do. It's bad notation. It's wrong. And there's a good chance you'll end up forgetting you were even taking a limit in the first place. This is x minus 1 minus 4. And that's x minus 5 square root of x minus 1 plus 2. I have limit as x approaches 5. I clean up the top. I get x minus 5 over x minus 5 times square root of x minus 1 plus 2 on bottom. Notice that the x minus 5 now cancel, and you would never have noticed it if you had multiplied it out. That's sloppy. I'm going to write that a little bit smaller. So if I plug in 5, I get 1 over square root of 4 plus 2 is 1/4. Got one more to show you, then I think we got one more to show you. Yeah, one more on this video. Limit, the complex fraction one. 1 over x plus 2 plus 1 over x plus 3. Always try sticking the value in, making sure, seeing if it actually gives you a value. This is -1 plus 1 over -3 plus 3 is 0 over 0. So we have a problem. So what we're going to do is get rid of the complex fraction part by multiplying through by all the LCDs. In this case, x plus 2. I'm going to multiply top and bottom by x plus 2. In fact, I'll make that a different color so it stands out. So this is limit as x approaches -3. When I distribute it to this one, it just turns into a 1. And then when I distribute to this one, I get x plus 2 times 1. Maybe I'll show that written out. X plus 2 over X plus 2 there. The bottom is X plus 3 times X plus 2. So cleaning that up, limit as X approaches -3. I've got 1 plus X plus 2. And again, leave it factored. You don't got to factor everything. Simplify. Hands going numb. Then we apply, we cancel out the X plus 3's. I get 1 over X plus 2. And now I can plug it in, it doesn't cause a problem. So this is how we find limits when there's a 0 over 0. And this is, we also talked about doing rational and just being able to plug stuff in. It's pretty nice. I'm going to pause or stop this video and continue in a second. I think it stopped it.